This is Frame by Frame Season 2, Episode 2. Today we'll be looking at neural networks a little bit more in depth. We're going to be looking at the different layers that make up a neural network and how the data is processed throughout it. At its simplest form, a node or neuron is a computational block that receives an input, does a little calculation in the middle, and then spits out an output. Let's take this analogy where a node is like a decision maker or a manager of a company. When it's time to make a decision, it will take in all the other opinions and experiences from the individual team members. The different team members might provide some different experiences based on their experience levels, and the decision maker, the node, will have to take in everything into account and give some different weights to who's having more experience and who maybe just doesn't have as much.
I don't know what to do. Do I go tell Joe, or I don't want everyone to keep blaming the wrong person?
I don't know what the best plan is, Bam. Oh, God. My mind is going a mile an hour.
That fast.
Oh.
Now, when a neuron is trying to make a decision, it's going to take in a whole bunch of different arguments and inputs that have different varying weights to it. It's going to add up all of these different components into a summed value and then send that value through an activation function. So at its core, that's all that a neuron would do. It will take in one or several different inputs and have different weights attached to them. It's going to add up all those parts and then spit out an output. Now, we can group some of these different neurons together and form layers that will organize our system a little bit.
No! Layers! Onions have layers.
Neural networks.
Have layers. Onions have layers? You get it. We both have layers.
So at the very beginning, we have an input layer. This is where we convert the image into a long array of numbers, usually at the pixel level. Now, this array can be numbers from 0 to 255 to tell how bright or dark the image is at each individual pixel. Or if it's an RGB image, we can usually send in 3 different color layers for an R layer, a G layer, or a B layer. This input layer is like handing an image to one person in an entire group. That one person is going to try to describe what they're looking at on the image just based on this one picture.
Oh, yeah. I know some of these words.
Now, it doesn't really send along a ton of information, but it does tell where the edges are or a lot of different textures. It's all based on just the patterns of the numbers and what it's looking at there. It's going to send that information to the next layer. After our image goes through the input layer, it's going through the main body of the neural network, which is usually referred to as a hidden layer or the fully dense connected layers. If we were to continue our analogy where we handed one person the picture of a dog or a cat in a room and told them to describe it to everyone else, try to bounce ideas off each other to see if this is a picture of a dog or a cat. Everyone in the room is allowed to put forth their ideas or their experiences to help explain if this is a dog or a cat. This helps build a confidence score within the model to tell if it really is a dog or a cat. These fully connected layers are responsible for when the model is deciding if an image is a dog or a cat. Each node is connected to the input layer before it and after it. So each layer forms their own sort of opinion based on the input layer and then spits out its own output layer into the next layer. So this is a great way in computer vision for neurons to guess if the image is an animal, a handwritten digit, or maybe a different type of car that's on the street. These fully connected layers are really good for guessing these images, but it's really prone to overfitting. Sorry to interrupt. Overfitting in machine learning refers to a situation where an algorithm learns to train on data too well, capturing noise and outliers, which leads to poor performance on new unseen data. This occurs when the model is too complex, fitting to the training data exactly rather than generalizing from it. As a result, the model fails to accurately predict on data outside of the training sets. An analogy for this is like having a star basketball player perform on every single game, and the team becomes too dependent on that one player and struggles when the player is injured or out. To help reduce the amount of overfitting in a model, we can introduce different techniques like a dropout rate. We will talk more about this in the future though. There may be a couple convolution layers in a network to help reduce the amount of size that each image is taking throughout the model. Now, I've talked about convolution before, but as a high overview of it, a convolution works like a magnifying glass. If you were to have a matrix operation, it zooms in on each individual pixel and it does some sort of multiplication to shrink the image, let's say by half or a quarter. It still preserves the images, the edges and different textures around the image, but it just reduces the size of it so that we can send more pictures and data through the model without eating up a whole lot of RAM. At the very end of the model, we have the output layer, and that's when the model has had time to comprehend all the different inputs and different clues that it's made, so it can finally decide if this image is a dog or a cat. It usually has a confidence score built into it so that we can determine exactly how confident the model is when saying this is a dog or a cat. Now, the last thing I wanted to talk about was recurrent layers. These aren't really used in computer vision that much, but they're used for a lot of sequential data. So that's like predicting a house based on the different aspects, time of year, how many people live in there. Maybe we're predicting a stock market price. And recurrent layers are used for when shifting data is occurring. As an analogy, let's imagine you're reading a book and you stop after each sentence and you try to remember what you just read. We can take that a step further and try to even predict the next sentence based on what was already read. In a real world, this would be applying like something to a stock market if you were to take in previous data and try to predict what the next day is going to look like, maybe the next hour is going to look like. We're not really going to touch much on here, but I just wanted to tell that there are different techniques like that that exist in neural networks.